The future of innovation lies at the intersection of intelligence and automation. I'm Sumedha Hiremat, NISPWI chairperson, and it is my absolute pleasure to welcome you all to today's Tech Talk, Smart Chip Design, How ML is Reshaping EDA. This event is proudly organized by NI IEEE Student Branch WIE in collaboration with IEEE WIE Affinity Group Bangalore section as a part of our special Tech Talk series for International Women's Day celebrations. In alignment with this year's global theme, Accelerate Action, today's session is about exploring how machine learning is transforming EDA, revolutionizing chip design, and shaping the future of semiconductor technology. As AI-driven automation continues to push boundaries, innovation in EDA are driving efficiency, speed, and precision in ways we never imagined before. We are honored to have a distinguished expert with us today, and to introduce our esteemed speaker, I now invite NISPWI Secretary Anusha to take over. Thank you, and I hope you all have an insightful session ahead. Over to you, Anusha.
Good evening, everyone. It's my absolute honor to introduce our distinguished speaker for today's session, Surya. She's an advisory engineer at IBM Systems Bangalore, where she has been a key member of the electronic design automation team since 2013. Surya holds a master's in VLSI design engineering from Cochin University of Science and Technology and specializes in standard cell characterization, gate level timing methodologies, and ML driven ADA solutions. With multiple US patents and publications, she has significantly contributed to IBM's server technologies and semiconductor performance. As an active mentor and advocate for women in engineering, she engages in industry panels and academic collaborations. Her interests include VLSI design automation, digital design, machine learning, and quantum computing. Today, she will be sharing her insights on the transformative impact of ML on EDA, highlighting key opportunities, challenges, and future directions. Without further ado, please join me in welcoming Surya. Ma'am, we are truly honored to have you with us today. The chat box will be open for your questions throughout the session, and there will be addressed in the Q&A session later. Over to you, ma'am.
Can you just confirm you're seeing the presentation now?
Yes, ma'am.
Yes, ma'am.
Okay. Sure. So let's get started. So good evening, everyone. Thank you for the warm introduction here. So with Women's Day just around the corner, right? It's the perfect time to celebrate the strength, resilience, and innovation that women bring to technology and engineering. So I just want to give a hats off to the WI organizers for putting this together. I mean, I've visited the LinkedIn page from the NISB, the student branch page, and I was seeing a lot of tech talks and webinars and hackathons you guys have been organizing. So that's very exciting to see all of those. And I just want to give a kudos to the teachers also behind it, the professors who is standing with them to do these events. So it's really like not just sharing the knowledge, right? It's also helps to inspire the next generation of leaders in technology with organizing these events and getting those insights from the industry or even from the other research institutes. So that's a great thing. So I just wanted to acknowledge that the true what do you say that commitment from all of you, right? And to all of you here today, it's just remember that every breakthrough, every innovation, and every step forward, it starts with curiosity and determination. So whether you are exploring new ideas or pushing the boundaries of research or just starting the journey in technology, know that you have the power to change, create the change. So that's what I just want to I'm try to do through this presentation. I'm trying to dive through like how machine learning is reshaping the electronic design automation industry. I just want to make sure through this session, it not only sparks interest in you, but also to encourage you to think big, stay curious, and embrace challenges as opportunities. So the future of technology is like shaped by those who dare to innovate, right? So why not let that be you? So with that, let me start my presentation here. So the topic for today is smart chip design and how ML is reshaping electronic design automation. So I've been with IBM for 10 years, as you heard in the introduction. So it's a very small timeline to be in the industry, but with the knowledge what I've gained so far, I'll try to give my perspectives, what I've learned for through all these years and all to you. So yeah, that's where we are starting with. So this will be the outline for today's presentation. I'm still hoping you guys can see the screen and the presentation clearly, right?
Yes, ma'am.
Yeah, thank you. So this will be the outline. So I'll just start with an introduction. We'll talk about today's chip design, how complex it is, and why you need EDA, electronic design automation for chip design flow. We'll talk about why this AI resurgence now, right? Why we didn't hear this term for a long time. And I just want to convey that how do the chip design and AI they stand against each other. We'll talk about some of the challenges in chip design flow and how ML is helping those like to mitigate those challenges what we are seeing in the chip design. One slider on how what are the large language models, what is helping EDA right now. Finally, the conclusion and what is the road ahead, what is the future, where we are going, and the last one, which is of more interest to you, all of you, like uh, when ML meets chip design, there is a big career boom. So what all kind of uh, uh, skills and everything what you have to set in mind, right? When you have your coursework and everything. So that will be the last slide here. Okay, so this is very introductory slide. I just want to bring you that the term semiconductor. That's like the humble mineral which transformed the world, right? The semiconductor chip has gone further than any technology in connecting the world. So if you think about in each and every corner in our lives, there is something involved from the semiconductor. If you think about anything in our day-to-day life, from a smartphone to a weather forecasting supercomputer, or even if it's like a very small device or a gadget with you, inside everything there is a semiconductor chip involved. So that's a basic building blocks of modern computation. And it's amazing to hear that the semiconductors are actually built out of sand. You know, right? The raw material for silicon is actually the sand. And there is a it's like a very tremendous process involved in creating that chip out of the sand or the silicon or the semiconductor. There is like an elaborate process involved in getting that chip manufactured and get into a product or get into an AI or cutting edge device what we see in our hands or what we see around us. So how this is possible, or what has been. So if you think about it, you might have all heard about the vacuum tubes in the history, right? Uh, those were in 1940s and all. So from there we have reached into a point we are seeing billions of transistors which goes into a chip. So in the next slide I just want to give you an idea of like where how complex today's chip design is. So you can see one picture in the slide, that is the IBM's Telem processor. So this is like so we call it the IBM C series, which is like a enterprise class server for us. So this microprocessor is announced in 2021, so that's almost like 4 years back in August. And I just want to highlight only the features of this particular processor, just to give you the clarity, just to get you the complexity involved in that. So this has about 8 processor cores. It runs with a 5 GHz clock frequency, and the design contains about 22 billion transistors and 19 miles of wires on 17 metal layers. Right? So can you imagine how much are we integrating to that particular chip? It's huge, right? Now, imagine the size of this chip. The size of the chip is like it's just the size of your fingernail, and the transistor sizes is in nanometers, and the wire width what we are talking about is like 1/500th of the human hair thickness, and 19 miles what we are talking here is like approximately 30 kilometers of wire. So that's what we have been using to get that chip out. And that chip has huge capabilities with that. It's with zero downtime and lot of features into that. But imagine the kind of complexity what we are building in right now, right? So in the very early days, this was all done through manual work. I mean, people used to sit and design. They write the VSDL, then they convert that into. I mean, it's being converted into gates, and it's all been like manual work. But over the time, things have been improved. So that then came the idea of like the chip design flow, right? So which means the chip design flow involves the steps taken to build that integrated circuit or the chip what we are taking about, by integrating all that billions of transistors to achieve a specific application. So the application could be suiting any particular requirement. It could be a microprocessor, it could be a router, or it could be a cell phone, whatever it is. So we need that design flow to be purely defined, and that's how that entire process works. So, and the chip design flow also has been evolved over the years, right? So my next slide is going to talk about why electronic design automation. So to implement a chip or a integrated circuit, what I've shown you in the previous slide, we need some kind of systematic flow, right? We need softwares, or we need it all started from small lines of code, but over the time, it's been like almost 50 years this has been getting evolved. So you can think about like those small codes of lines get built into smaller software, smaller applications that help in aiding that chip design flow, right? So in summary, designing a chip is the task of figuring out how to make the chip to do what it want to do. So as with billions of transistors in that, the automation of all these, without automation, this is impossible. So that's where the term, or that's where the electronic design automation tools comes into picture. So it's basically what it is basically doing is automating the design of electronics. So we do make software which is used to design the chips. So we always talk about the flow. So I'm sure like most of you will be doing minor projects or even your major projects with the FPGAs, or all those of ASICs kind of environment, right? But all what you do you'll be running, you'll be taking an HTL, running through the stages and getting to a bits and all those files what you generate, right? The bitmap file what you generate. But in the back end, all the software which takes care of everything is the one who is actually doing the workhorse here. So that's what the importance of electronic design automation comes in. So it's very crucial for the semiconductor industry, or integration of all these tools and methodologies. It helps to produce the faster designs faster. It will generate bigger designs better, and create more complex designs simpler. So that's the idea behind EDA. Now, so one of the you all are very familiar with the Moore's law, right? So over the last 5 decades, there was an exponential expansion in the semiconductor technology, and it's all been predicted with Moore's law. So uh, the transistor count will double every 2 years. So that was a prediction, but we are much ahead from all those things right now. So it's Moore's law is slowing. So what we are seeing is more than more. That is what is playing a key role going forward, right? And how is EDA enabling this move slow so far? So there could be, over the time, there could be a lot of advancements in the technology and all those space which help the move slow. But at some point, the electronic design automation and the tools and technologies what we use to build these tools then take up the stage. They were we were able to do like new design methodologies. We could do turnaround time advancements. It could be the process technology enablement. All those key factors will come into picture, and that was one of the key factors which enabled move slow for some point. So that's another aspect which we have to think about here. So I'm sure you might be familiar with the chip design flow. This is a very simple concept of, you start with writing the spec for your chip. You then do the RTL. It's basically converting the high level description language into the gates, just to give a very just to remind you about what the flow is. Then you make the chip testable. Okay, so that there comes basically different aspects in this chip design. So you have the front end design, you have the back end design. The front end design is what is known as the where you write the HDL, or you write the hardware description language, which describes the architecture for that particular chip. And the next step is basic time. The time consuming aspect is verification, in which we want to make sure the gates or the design is going to work as per our requirement. So that is a time consuming step. It involves even understanding the timing, the power, all that aspects. We have to meet the power performance and area metrics. Everything has to be achieved through that particular step, right? The next phase is the laying out the chip and double checking the layout, and finally making that design into a silicon, or you have to manufacture that as a chip. So those all comes in the back end side. Again, in the back end also, we can categorize into different buckets over here. Like it starts with the logic synthesis, in which you convert that, where you do the high level synthesis, you convert that logic into gates. Now the gates you can think of like these are just symbolic expressions. How these are actually going to work in the hardware will be like through shapes. So you map these gates into the layouts. The layouts are basically the shapes or what the connections which finally work in the hardware. So all that mapping, how you place the gates, how you route them, how you give the connectivity to them, that is all going to happen in the physical design stage. And there is a general checking, or there are some timing analysis steps what we have to make sure to to ensure that the chip designs or the chip works in the desired frequency. So those there comes the static timing analysis and all those steps. Finally, there are a lot of checks before we send that information to the fab, or before we sign off everything. We have to make sure it meets all the design rule checking, like we are actually putting the layouts and all the levels and layers in proper format without I mean, the DRC has to be valid, everything has to be cross checked, and that's where how we are sending the chip back to the lab. So you can think of like this process, what I'm starting from here to here, for a complex chip like what I've described in the first slide here, the telem chip. It takes about 2 to 3 years. There will be like a lot of designers, a lot of backend engineers, everybody working together to get that chip finalized and get to the industry. So that's how the old processes, and that has been historically being done, and over the time there were a lot of improvements done with these technologies. Now, with in the last couple of years, maybe a decade or more than that, we started hearing the term AI, ML, DL, everything, right? And all of these have getting a lot of we're using a lot of opportunities from AI and everything back into the chip design flow as well. These are all the buzzwords, and it's like ruling the world right now. So everywhere we start hearing things from AI. So just in this slide, I just want to get that why we are hearing this AI resurgence now. So just a recap of what happened. So AI is not a new term. So if you look into this particular slide or the chart here, in 1950s itself, this term was already coined, right? So we all have heard about Alan Turing, who introduced the Turing test, which is a test that challenges whether a machine can think, can it answer questions like a human being depicts, human being being like a human being, right? Can it do that? So it started from 1950, so it's more than 50 years or even more than that now, right? And later there was like a slow period in case of AI. So the major reason at that point was like majority of the algorithms or all the things what we have described at that point was not able to implement, right? So in 1980s, what we start to hear was like this is again, sorry, in 1990s, what we started to hear some boom or some sort of uh, some of these words again started coming back. So that's the time in 1997 is where IBM's Deep Blue computer that beats Gary Kasparov. He was like a he was the winner for chess for a long time, and that's a time when IBM's Deep Blue computer actually beat him in the chess. So that was like a big news at that point. So that the back in that, it was all powered with AI. Again in 2000s, so things started getting some traction, and late in 2000s, IBM introduced Watson is nothing but a question answering computer system that is like able to answer questions when you ask it in the natural language processing. So like IBM's Deep Blue, Watson was able to beat the Jeopardy contestants, two of the Jeopardy contestants at that point as well. So slowly things started kicked in, and one of the reasons being for that was like, as I mentioned, all these algorithms what AI uses will need a lot of computational capacity. It needs to process volumes of data and the processing speed. So till that point, we never had computers or computers or processors which supported that much computation efficiency. So slowly by 2000s and around that time, our technologies and tools and even chip design flow got matured, and we got to a point we are able to um, uh, design complex neuromorphic processors. And in these with these neuromorphic processors in place, we can actually run these AI algorithms, and in that, with that computational efficiency what is required. So that's where the AI resurgence happened. So also there are like a lot of open source frameworks started coming, like PyTorch, TensorFlow, which many of you are aware as well, right? And again, it's just not the faster hardware we have. Sometimes they're augmented with GPUs, the specialized arrays of processors. So that also was helping to have the AI algorithms run with a much more capability there. So with all those framework, with everything came in right time, and we started seeing that ML and chip design is coming hands in hand. So the next slide is just talking about that same thing what I've described earlier. So you can just think like it is not, both are helping each other, they complement each other, right? So for AI for chip design, so uh, all these chip design is now driven by AI, which means that it is revolutionizing the electronic design automation by making chip development faster, smarter, and more efficient. Now, coming back to uh, with the chip design, with the advancements in chip design, we are able to manufacture, or we are able to uh, do specialized AI hardware. And with these AI hardware, we can run more AI workloads, which we can, which actually needs custom chips to run deep learning models faster, more efficiently, and at lower power. So it's actually going hand in hand. It's not like it's like one is helping the other in making all these advancements, and in all these getting all these boosts what we are seeing in the semiconductor industry right now. So with that, yeah. So with that, let's look into some of the aspects, like just go into some of the details, how ML is reshaping EDA, right? So I thought I'll just pull some of the challenges in the chip design flow right now, and probably we can talk about what are the challenges in each of the field, and what are the techniques available in ML, or what is getting more used in at these times to mitigate those challenges. So that's how the next couple of slides are arranged. So first thing, as I already talked about, increasing design complexity, right? Um, so we see billions of transistors, and making the manual optimization is impossible. So we also see complex architectures, the multi-core, the AI accelerators, all these require sophisticated design techniques. And we, as I mentioned, there will be like heterogeneous integration. You have to integrate the CPU, the GPU, the memory on the single die. All these aspects will complicate the design. So that's a pretty dominant space where AI can play a crucial role. So a lot of algorithms are in place, and a lot of papers and research and publications is already out there. So there are AI assisted design, space exploration, which can speed up the architecture selection, and even a lot of ML based EDA tools are there which can automate the optimizations that were previously manual. So earlier we had to switch between multiple options and then try what is that optimal solution, what we're going to get. So right now this is all done uh, through the ML based EDA tools. So that's how it is helping the. Coming to the next one, the PPA, that's a power performance area trade-off. The main thing which how the chip design is driven, right? So we always have to balance the power consumption, speed, and chip area. It's very difficult to achieve that low power and high performance designs, especially for the edge devices like your phones and all that ones which where we cannot have the higher power consumption. So the power integrity issues is another set of things which limits the scaling and all these trade-offs. So here also there are AI driven power estimation models which can predict the power model consumption much earlier in the flow. We don't have to run through the entire flow to understand how much power that particular chip is going to take. So we can use the previous technology nodes or previous designs. From that we could predict, we could write out models, or machine learning models, which we can use in the next iteration and kind of get a sense of how much power this design is going to take. Um, the ML assisted place and route tools, they can optimize the wire length, reducing the power and delay. So that also is again is a big thing which is coming and helping us for these PPA trade-offs. Going down, timing closure, as I mentioned, this was one of the major focus when we always design the chip, right? So always we have to meet the timing constraints. We have to make sure the chip is operating in that particular frequency what we're designing it for. So it is becoming harder to meet the timing constraints, and we have to encounter the process voltage and temperature effects, which is going to affect the chip's performance. So you can think about, like, even though we manufacture a chip, and we design for some sort of timing, it may not work in the same way as in the hardware. So you may see a lot of variations which can come in, and it can affect the delay of the inverter or delay of the small gates, what you actually built in, or what you actually seen through the chip design flow. It may vary from that. So we have to encounter all those aspects inside it, and which means that we cannot just go for the traditional static timing analysis. That is again computationally expensive. So here also a lot of algorithms have come in. Again, one of the things in the back end is like, we have the standard cells and layouts which we provide as a basic building blocks for all the designs, right? So even uh, the timing models what we generate for different PVT conditions, we don't have to generate for all the corners. It might be time consuming to simulate all the corners and get the dot lips, or get the delay models what you need for the entire design. So there are ways you can predict from two corners or three corners, you can predict a newer corner delay. So it has become so mature in this time that you will get you can get rid of that simulation time and get things much faster. So the other aspects which is playing a main role here is the graph neural networks, which can actually predict the timing violations much faster than STA. So basically, you can understand the nature of the graph and can predict. So this is like even efferent. Say, for example, you have not routed the design. You can even think about predicting the timing analysis in that routed design much efferent by providing. We can actually train that kind of different types of paths or different types of uh, previous scenarios in the previous designs and everything, and we can create a model out of that. And with that model, which we can actually predict the slack. Now with that, we can actually optimize the algorithms to do the placement route to get to an optimized slack at a later point. So graph neural network is currently gaining a lot of attention, and that's being used in a lot of predictions of timing violations. The ML based clock tracing, this is that is again to improve the timing convergence. That's one another research area which is actively going on now. Coming to the design verification, so it's just that we write the VHDL, we map them into gates. That's not the case. We have to verify the HDL. There is a tremendous amount of work going in the background to do the verification of that logic what we have written. So it involves functional verification as well as formal verification, again the physical verification as well. So majority of the time in the chip design flow is consumed in this verification side of things. So there are a lot of simulations which will be handled, like you have to do even base simulations and everything to understand how the logic is working correctly on these large designs. And these simulations sometimes takes a lot amount of time, and sometimes debugging and understanding the cases is more manual, and it is actually error prone. So a lot of advancements have come in the verification aspects as well. With the advancements with some of the algorithms, what we can do is we can kind of prioritize what is a critical test case, and we can focus more on that critical test cases and use that critical test cases to verify the design. And even using the LLMs, we can actually assist. They actually assist in the automatic bug detection and even for the RTL debug, what I mentioned as a third bullet here. The next major area is the process variability and manufacturing challenges. So with the technology not shrinks, um, the manufacturing defects and yield losses also increase, right? And even the process variation impact the device performance, as I was mentioning earlier. As it is going to shrink, all these variations as getting more and more impact, and it can affect the timing what you've already designed the chip for. So the post silicon tuning also is very costly, and that is also time consuming. So a lot of advancements have come in that areas as well. So there are ML based yield prediction models which can even predict the uh, yield, and it can optimize for the design for manufacture. So these can be done even prior in the design itself, and we can actually learn from that hardware and bring that into the model and kind of get that yield better. um, the AI driven defect detection, that again helps to improve the manufacturing yield. A lot of research is going on that areas as well. Coming to the routing congestion and layout optimization, that was again I was telling. So right now in the advanced nodes, the interconnect delay is dominating the performance. So whenever the layout is the design is more complicated, it will get um, more congested. So it will be harder for the routing algorithms to solve that problems, and it can affect the signal integrity as well. The traditional algorithms it may need more. It has to struggle more to optimize for the power performance area and area metrics. So lot of ML algorithms, including the reinforcement learning, and lot have come in this area as well, to help the routing congestion and the layout optimization problems. Now, coming to the post silicon debug and performance tuning, right? So there could be chip failures in the silicon prototypes. They are also very hard to debug. So the aging effects. So there are ML models which can actually predict the aging efferent, and we can correct that within when we do the designs as well. So those sort of ML techniques are also as a part of the flow right now, so that helps to mitigate these problems as well. The other bigger problem what we see right now is longer design cycles. As I mentioned, to bring to the market a chip like what I've showed earlier, it takes 2 to 3 years. And imagine to run that, sometimes to run the once we get into integration and get the chip run into a full mode, it might take a lot of time, right? So and even if the risk, the cost for mask and all the fabrication cost, everything is expensive. So we have to make sure the final mask what we are giving to the foundry is error prone. So we cannot we always have to guarantee that. So the design iterations is really taking a lot of time, so because of the traditional tool limitations. So a lot of advancements have happened in this area as well. So there are a lot of advancements happen in improving that longer design cycles as well in the ML field. So just to put together all of these together, like these are the bits and pieces which you can think of, like where ML is helping EDA or helping the EDA tools to make the chips faster, efficient, and smarter. So it's mainly the design space optimization. It will help to automate the repetitive task. It helps in the predictive analysis and error prediction. A bunch of them helps in the verification and validation aspects as well. A lot more has gone into improving the power efficiency. Like we can efficient predict power and get to tune your design based on that. Then again, speeding up the time to market, as I was already mentioning, and a lot of enhancements has gone within the EDA tools to insert custom solutions, so that we will get the better chips out to the foundry. So that's a very high level summary of what I described in the previous slides. I'm not going to the technical details, but again, if I take the chip design flow, right, just to give you the kind of algorithms what is getting used in each of these steps. I'm not going to very detail here, but starting from the specification, you can see like the Bayesian optimization, graph neural networks, they play a key role in the design space explorations I was mentioned in the previous slide. So just trying to map the key algorithms, and some of them you might have heard, and these are the real applications, or they're getting applied into the actual applications within the chip design flow. For example, for the RTL design and high level synthesis, LLMs are getting a lot more used right now. It's mainly for assisting to write the HDL. So imagine you have to write hundreds and thousands of lines of code to generate the architecture, right? So how if we get help from an LLM to write that code? So those sort of capabilities are available right now. Again, the AI driven synthesis tools, how to get that optimized mapping of gates. We can use the AI tools when you do that high level synthesis and RTL mapping. Logic synthesis and optimization, that's another area. So one important thing here is, like, you can have a supervised learning for the synthesis parameter tuning, which means that you can actually learn from the set of parameters what you had in the previous iteration or in the previous runs. You could actually come up with a set of parameters which will help to optimize the design faster. So that's one of the emerging trend what we see during the optimization process. Even the neural networks is helping a lot for logic minimization and boolean optimization as well. So a bunch of there are some research papers towards this work as well. Now, coming to the placement route, I already mentioned the deep learning techniques is really helpful for the placement optimization. It's like an action and reward based learning, which we can help which can help the real placement of the gates in the design. Now, coming to the timing power analysis, we already talked about it. So we have the GNNs for the fast STA approximation, finding the timing metrics much efficient. the regression models. This I was explaining for the standard cell, the timing and power models. We could actually use the regression models to predict for a newer corner or a newer condition with that modeling in that. Again, for the DFM and yield prediction, unsupervised learning is one such aspect here, and even the for lithographic pattern recognition, deep learning, there are a lot of deep learning techniques available, which can be used on these stages. Again, the verification, as I mentioned, it's most of the formal verification property checking is AI driven right now, and the failure root cause analysis, that also is ML based, so it will help to analyze, and it will reduce a lot of manual errors and things like that in the design flow. Coming back to the sorry yeah, coming back to the post silicon validation performance tuning, again, there are a lot of tools and tools which we can help in the data mining after the post silicon once we get the post silicon data. So it's all being assisted by AI and ML right now. So just coming back to the, so we all talked about the good side here, right? We have a lot of algorithms, we have a lot of techniques which we can borrow from AI, from ML, and we can use that in our areas. But there are always challenges associated with that as well. The first of all, the data availability and quality, right? Most of these algorithms need large and high quality labeled data sets. So that is not always the case. So if you're starting at the starting point of any of the technology node, right, you won't be having that the bigger availability of data. So it will take some time for the design to get mature, and you have to get starting some of the data. Otherwise, you have to rely on the previous technology node to get that data. So that's always a concern. And that's what I say. So even if you take the data from the previous technology node, that's of a challenge, because the design variations, it will be huge across the technology node. So if it was like a similar node, we could probably borrow those information, but otherwise it is very difficult to switch from one technology to another technology and use the data in that aspect. The model interpretability and trust. So we always one of the problem with the AI or ML is we always see that as a black box, and we don't know what is really happening inside, right? So the confidence on how the results are is always, it always, we always wanted to the result should be explainable. So if we are seeing some trend, so for some particular design, something we are seeing, we should be able to explain that trend. Unless we are not able to explain that and relate back to what we expect, that is not clear, or we cannot build that trust with the model. So that's an important part. The results are always not trustable, so we have to put some effort on understanding the data or understanding the results what AI or ML is giving us. So most times, it's most times a hybrid approach. We go with the traditional rule based approaches and we combine the ML approaches. Sometimes when we implement our algorithms within the tool, what we do is, like, we have the traditional approach, the ML based approach will be a kind of a parallel flow, so that we always have the confidence on the rule based approach, and wherever ML can give some speed up, we can all the time cross check with the rule based approach, and that will help us to validate the results as well. So we don't want to bypass the rule based approach all the time. We just do as a parallel mechanism for the implementation. So that's again what is the that's a point for the next one as well. So we always try to integrate with the existing flows. We make sure it is compatible with the traditional EDA tools and algorithms, and it is always important to scale that ML models across different design process. So that scalability also is a huge problem at this point. Computational cost and efficiency. Traditional ML models that require significant computational resources, and that's always a concern sometimes, because we wanted to have a good computational efficient machines to run these algorithms and have that. So that is not always the case. So that is one of the bottleneck, or that is one of the concerns, some of the at some points what we will be having. And there is always a trade-off between the model accuracy and the runtime performance. So we have to keep in mind that the model accuracy and the runtime as a trade-off when we have all these ML algorithms implemented. So just talking about, so we all are hearing about the large language models in the last couple of years, starting from the GPT, then uh, the Granite is IBM's LLM. The Granite 3.0 is the latest one what we have, and even Google's Gemini is one out there, right? So we hear a lot about all these large language models, and we started adopting the large language models also for different EDA applications. For example, the first and major use case is the assistant chatbot, as what you see in the case of a normal LLMs, right? So even for the designers, we have implemented a lot of chatbots so that they don't have to search around or ask questions or things like that. So they can use existing repositories and query or check their they can ask their questions and get answers. So that's a first and foremost thing what is being done in majority of the cases. So they can ask the tool or ask the repositories or ask the code repositories on what to be done or what is the solution if I face something like this in the design. So that's a very first thing. The next one is code assistance, as I already mentioned in the HDL, the hardware, the HDL languages and all, right? So there are code assistants available which can actually write the HDLs for you. So you just have to, and there are even a lot of things which even can write out the HDL for you if you just have a schematic or just have a picture for that. So it has advanced in such a way that it is becoming more efficient to write the code rather than having a lot of manual code interventions. Now, the HTL verification analysis, that aspects also, the LLMs are starting to help a lot. Logic synthesis, again, on the optimization side, there are aspects which LLMs can be used right now, and physical design is some logic synthesis and physical design is not really getting lot of help from the LLMs because it's because of the complexity of the problems and how the LLMs are architected. So that's something it's still under research, and we may have to uh, try more or get more research and work to utilize LLMs for these two areas. But otherwise, the chatbots and code assistants are really in the top side when we come to the large language models for EDA side. So just coming to the conclusion, I liked this particular, this was there in the IEEE notice, right? What is the road ahead, right? So if microchips wrote autobiographies, they would title this chapter, The Age of Self-Discovery. So that's what is the road ahead, right? So far we have been using AI to power the EDA tools, and going forward, what is the right? So it's going to be an autonomous chip design and self-optimizing architectures. That's where the future is. It means that combining ML with hardware design to create optimized architecture. So that will be the future. Even how we can leverage the generative AI for chip design. So as I mentioned, it's not being leveraged that efficiently right now. So that's going to be one such research area, how we can use the generative AI. For example, can we create new circuit architectures? Can we have new micro architectures? Can it predict all those things? So it's all where the research is going right now. um, Now coming back to the self-optimizing EDA flows, right? So right now we are having a lot of algorithms to do this optimization. So can the model selection, even the hyperparameter tuning, can be automated? So we have a model, can we change the whether it will be able to change the model on the fly? It can change the hyperparameters on the fly and get to a perfect solution. So that's like the self-optimizing EDA flows. That's going to be the next thing coming in. Now, the quantum computing and ML. So the potential of quantum enhanced ML for large scale design optimization is again the next future thing. So all these are the next things. So it's going to be an age of self discovery. So far we have been getting a lot of help from machine learning, but going forward, um, how can we have that, what do you say, it's more like an self, it's all being like a self driven. So we are actually entering an era where the chips don't just follow the instructions, they will analyze, they will predict and enhance their own performance. So that's where the future is going to be. So with that, I'm just coming to my concluding slide here. So from silicon to intelligence, right? So what is there in the career front, right? You all are doing your coursework, and I mean, the journey ahead is like so exciting. There are a lot of increased demand for skills, like you need to understand the core semiconductor, you need to have that chip design knowledge, That's very important. Your basics is the best, right? And the programming and the computational skills, that's C++ or whatever languages you're familiar with, Python, everything is getting a lot of importance right now. And understanding the emergent technologies like quantum, and even the future trends in those. So that is very important. Keeping up to date with what is happening in the industry, soft skills and industry readiness. When you come to the industry, you cannot be just shy, like I don't know this term, I don't know this, I don't know this. So you have to be self prepared, read a lot on the side, get read papers and advance things what is happening in the industry, so that you won't be you don't feel that gap when you are in your when you're doing your research, or you're doing your the bachelor's or master's or whatever degree it is. Now the core, the main thing here is like, it will be like an interdisciplinary expertise. It's just not the knowledge of one thing, it will be like a combined knowledge. You need the semiconductor knowledge, how the design is working, how the circuit is working, that is important. At the same time, you should be able to handle the ML or AI optimization for the hardware. So those are the key. It's like more like an interdisciplinary expertise what you have to build up to shine in this field. And data scientists with VLSI knowledge is really good. The VLSI and ML algorithm developers, that's going to be the next set, which is going to drive the future, right? So all these are the skills and expertise what is in demand in industry right now. So whenever you are having your coursework and all those things, you can focus on the right things and drive towards like what you want to be. So I think with that, that's all what I have. I think I exceeded the time also a little bit. uh, so with that, I'm just coming back. And yeah.
Thank you,
um,
ma'am, for such an insightful session.
we can go with the question and answers if anything is there.
Yes, ma'am. Now we are open for Q&A session, and we have a question in the chat box. It states, what are the challenges and opportunities of designing chips using new materials like graphene or nanotubes?
uh, those are mainly so I think the nanotubes or a version of nanotubes is already what we are working on right now. So it's been already proved in the industry. So I guess it's under, I would say it's mostly under process. I mean, it's under production. It's going to be in production soon. But we have not ever heard anything on the graphenes and all those things for a what do you say, for a enterprise kind of systems. But nanotubes and nano sheets, those sort of things is what we hear in our trends right now.
Yeah. Ma'am. Uh, any follow-up question? Okay. I think that's it. If anyone has any more questions, they can raise their hand and ask the question. Okay, Nirup, you can go ahead and ask your
Am
question.
yeah. Hello. Hello.
Huh,
Yeah, I
you
can
are
hear
audible.
you.
Yes, you are audible.
Okay. Ma'am, like as we know that EDA is heavily dependent on like high quality data, and often we can say that it's a proprietary data. So which is often owned by a few semiconductor companies or like kind of things. So I like other models like other ML domains like LPs or computer vision where we have the massive open set data exist. EDA is scarce of data. So keeping this in mind, like how can I trust a synthetic data playing a role in generating a realistic, the circuit designs for design? Next question. And second question is, uh, we don't have a proper federated knowledge or a data set to train any models or ML model. So how can LLMs be trusted, especially in these kind of fields, to get even suggestions? Like
I couldn't get all that what you asked. Is it Nirub, right?
yes, ma'am.
You
Yes.
were probably if you can yeah, repeat the first. I mean, at least the sometimes the first one that would be better. It was breaking in between.
Sure, ma'am. Sure. Like I will.
So the
Like
first one
we
is
know that
about the
chip design.
availability, right?
Yes, ma'am. Chip design is oftenly, data. I mean, chip design data is often a proprietary, making it hard to
Yeah.
train the ML models. So, how can we trust a synthetic data playing a role in generating a realistic circuit designs for, for training ML models and all?
So, what at least within IBM, we have a lot of in-house tools. So all our tools are in-house, and what we work majority is the in-house actual design circuit design data what we have. So it's not like cooked up data or anything. It's real data what we are playing with, and we tune our algorithms with it. Yeah, it's all proprietary data. It's not easily available outside. But there are a lot of open source sets also you can play around with, right? So you don't have to. So, are you asking about from a industry from a academic perspective, right? That's what the question is.
Yes, ma'am. Yes.
Yeah. So I don't think you have to. You can even still play around with that smaller data sets available with you in open source. But the key here is like during your academics or your coursework, right? um, the skills what you build is important, right? It's all about what you learn as a basics on understanding of that steps or how the algorithm works and all those details. So it's just not about the data as well. But once you enter the industry, you will have that enough enormous data to play around. But all that you have to worry about is uh, like how you understand all the details in it right now. But once you are into the any of the companies, you will, I'm sure, like you will be exposed to lot of data what they are providing. And the other opportunities probably through internships you can get into the companies. And yeah, that's where one opportunity where I can think of, you can you can play with some realistic data. But otherwise it's proprietary, and it's not really accessible to the outside world.
Yes, ma'am. Thank you. And my second question is like keeping this in mind, about the data set. So we don't have any federated knowledge kind of data sets to train any model. So how can we trust an LLM model to get even a suggestion for, EDA?
um so this also is again based on your experience outside, right?
Yes, ma'am.
Yes, so I think the same answer holds for this one as well.
Yeah, okay.
Yeah, it is.
Okay. I
It's not.
got
Yeah,
it. Got it, ma'am.
it's not something which we can do because it's all proprietary. We cannot provide that data outside. But yeah, once you are in that research or kind of framework, uh, probably it is easier. Yeah, the data is
Okay.
always a problem.
Yeah. Okay. I got it. Got it. Thank you. Thank you.
Yes. Thank you, Nirup. Now, Vishak, you can go ahead, unmute yourself and ask the question.
Hello, ma'am.
Hey, Vishak.
Ma'am, I have a question. So, AI-driven design relies on massive data sets. So, this can reduce the transparency and make debugging a bit challenging. So, how can we leverage AI in a way that it enhance the chip design, like, and while maintaining the interpretability and the ease of debugging?
um so that's for the yeah, so for any machine learning or any problem, right, the first thing is your data set, right? um so the one thing which I have seen around is like people just trying to work on the ML models, but they may not be knowing the background of what they're working on. So that is really a bad thing. For example, it's just not easy to jump into a problem if you don't understand the domain. Say, for example, you are a you're going to work on a placement and routing problem. If you don't know if you don't have the understanding of placement and routing, then you work on that ML side. That's where the problem is, right? So I would suggest, or at least you all have to keep in mind, is like all our basics and all our knowledge in the semiconductor or the electronics and all that basic maths. everything is very important here. It's just that you have a tremendous amount of data and you can make assumptions from that. That's not the case. You need to understand the domain first. You need to have some expertise on that. Then you can actually play around or try to apply the ML algorithm. So you need the traditional approaches and understanding in all those, and then try to apply what ML to that. So right away starting with an ML is not a good solution here. So that's what is helping the industries as well, because people in industries like working on that traditional problems for years. And when this resurgence or when the surge in AI came in, right, they were able to switch and understand. They could take the best out of that and implement into implement as a solution for the traditional problems what they have. So that's what is important. So that's how you interpret the data as well, right? So I think that's the main point here.
Okay, thank you.
Thank you, Vishak. Now we have two more questions in the chat box. The first one is, how crucial is a master's degree for someone looking to enter research-oriented roles in ML-driven EDA and chip design?
I would say it is not really crucial to have a master's degree if someone is wanted to enter into that role. It's all about it's all about your passion, right? So um, there are specializations in the masters which can help. For example, it could be a masters in the VLSI, which again takes you to a lot of concepts in detail. But I don't think it is not really a necessity to take a master's degree to enter ML driven. I mean the EDA or any such field. If you are already into that, after your bachelor's, you're actually good. You can start your career from there. And there are opportunities within the industries as well. You can go and pursue masters along with your job. So those options are also available. So I have colleagues, or I have my juniors who are doing the same. So it's not necessary you have to take a masters and then get into the industry. It's all about the skills what you have built. It's all about how much you understood from your coursework, um, how you're actually applying that. So that is going to be important. So just try to understand, or get an understanding of what you're learning. Actually, it's just not for the exams. It's just try to connect the dots with what is happening around. I'm sure, like with internet and a lot of things around you, you will be having a lot of avenues to experiment the things what you learn, right? So all those is going to help. And build that programming skills or whatever is needed. Take courses on the side, so those all will be helpful. So it's not like you have to do a master's degree to get into this domain.
Yeah. Thank you, ma'am. There is another query from Praswana, ma'am. That is, any inputs for students to get internship in VLSI field?
So I can talk from IBM side. IBM has tie up with some of the colleges, which I'm not sure the NIA. This is the NIA Mysore campus, right? I'm not sure if it's like the case. We have types with some of the colleges which we go and take students for internship. Probably you can talk with the spokesperson with IBM, and you can just give a try for that. So that's a normal procedure. We go for internships. It's all based on different companies and their strategies. It's not. It could be not as easy as like entering as an internship from as an outsider. So it could be mainly through campus placements or campus driven internship recruitments.
Okay. Thank you, ma'am. We will be wrapping our Q&A session now. Thank you all the participants for asking your questions, and thank you, ma'am, for promptly answering them. Now I
Thank you.
invite Anusha to deliver the vote of thanks. Thank you.
The best way to predict the future is to invent it. Alan Kay. Today's session has shown us how the future of chip design and technology is being shaped through innovation and the transformative power of machine learning. First and foremost, we sincerely thank Surya Ma'am for sharing her invaluable insights on smart chip design and how machine learning is reshaping electronic design automation. Your deep expertise and perspective have enriched our understanding of this fascinating domain and inspired us to explore the future possibilities in this field. A heartfelt gratitude to the IEEE Bangalore section and Dr. Usha Rani, IEEE Bangalore section chairperson, for the continuous support, to our core team for their efforts in making this event a success, and to all our attendees for their enthusiastic participation. Your engagement and curiosity make events like these even more meaningful. Once again, I thank everyone for being a part of this event. Thank you, one and all.
Thank you.